and a happy Thursday. I hope everybody's safe and well in these times. I know we're going through difficult times, but at least the oil prices is about 35, that there's some light at the end of the tunnel. I am Shivani Wise. I'm Technical Services Engineer with Odessa Separator. Have been with the company for about 3 years now. And we have Gustavo with us today.
I'm Gustavo Gonzalez. I'm the Technical and Sales Manager for Odessa Separator, and I have been with the company for around 7 years.
Yeah, thank you for y'all's time today morning, and definitely would like to thank Don Ann for inviting us and giving us this opportunity. What we're going to go ahead and discuss today is sand control or homogenization. Go ahead and explain what the industry faces today, especially when we have horizontal drilling and hydraulic fracturing that has changed the face of the industry as far as technologies go. And with the higher demand of horizontal drilling and hydraulic fracturing, so has the demand of sand increased. So what have we've seen in the past few years is the demand of sand or propan, frac sand that we call these days, is we can see in just about a few years in 2014 up to 2018 has dramatically increased. The reason behind this is also the length of the laterals has increased. So we went ahead and drilled laterals for about 5,000 foot in 2014 versus these days the lateral foot is 8,000 foot. So your propan per lateral foot has increased. And if we see the graph on right hand side right here, we can see in 2014 the pounds per foot was almost less than 1,000 pounds, and now we can see in 2018 it's about 2,250 pounds per foot lateral, which means we've increased more than double in just a few years. Also, let's see the graph on left-hand side. So this definitely shows all the basins, and we can see here the Permian Basin that is in blue. We can see how dramatically the demand of the total propan has increased, which today, or let's say last year, was almost about more than 75 million tons total frac sand, and it's forecasted to grow consecutively in the following years. So how much of a sand do we use in a well in the Permian? Let's say we're having 8,000 foot of lateral. We're using 2,250 pounds per foot lateral, which means to complete a well in the Permian Basin, we're using 18 million pounds of sand. And if this was to hold true, just to complete the drilled and uncompleted wells, which in 2019 was about 8,500 wells, we're going to use 153 billion pounds of sand. Well, just to give you an idea how much sand we're using, just in numbers.
And, just to complement that, Shivani, I mean, what you mentioned is really, important to understand what's going to happen with the sand. I mean, we're just injecting and fracking these wells. The sand can disappear. And now you're going to cover a little more of this. But like you say, 2014, I remember we used to have just 28, 24 stages. Right now, 2020, we're doing 62 stages. In some cases, we're doing 72 stages. The lateral length increase, but the number of stages are related to that proportion as well. What it means, more consumed of the propane that we're using to frac those wells.
Exactly. And just to go ahead and have that in numbers for, let's say, go ahead and see what is the percentage of overall U.S. versus the Permian Basin that we're talking. How big is big? As big as Permian can get. We're using 37% to 40% of overall U.S.'s demand of propan sand just in the Permian Basin, which is compared to two of the other bigger basins, that is the Eagle Ford and Marcellus combined here in the Permian Basin. And if we were to compare that to the rail cars per day, it's like we said 500 tons per day, which is 600 rail cars could be filled full of sand, and that's used just per day. And that's just predicted to go higher. It's supposed to be 45 to 50% that Permian Basin itself is going to use for the whole U.S. demand, which means that right now it is 68,500 tons per day. Demand going higher, it's going to be about 163,000 tons per day. And that's what we can see is with the production, where we in 2018, just about a couple years back, it was 2.8. The oil production itself has increased to 4 million to 3.8 to 4 million barrels per day. So increased production, increased technology has its cons, which is increase of propan sand, and this sand, like Gustavo said, is not going to disappear. So the main question is, how do we go ahead and control when we're not only having your natural formation sand, but we are inducing so much sand in just per well, which we saw was 18 million pounds in a well.
You know, one of the things that I like, I know you already covered the majority of this topic, but I'm more like graphic. I need to see like a photo to understand a little more the severity of what we're talking about. So you mentioned everything, 600 rails is what we need, or what we're feeling. It's more like 21 million pounds of sand that we use per well in a well that is maybe 8,000 feet, 10,000 feet on the lateral, or 12,000. We're doing like 62 or 72 stages. So that is equal. Let's say on the flow back, we're getting 30% of the sand back. That 30%, it will fill 2,715 move joints or tailpipe, whatever you want to call it, or that is equal to 84,165 feet of tubing. So what we're saying is more like with the amount of sand that we are using to inject or frack on these wells, we can fill the entire tubing for 8 wells. That is going to be the analogy. It's almost equal to 8 wells based on the proportion of what we're doing. And like we say, the sand, you cannot disappear the sand. A portion of the sand is going to be in your reservoir and in your formation, but slowly, every time that you increase that drawdown and you're pulling harder on your ESPs before you do the conversion to rod pump, or like on the bucket that you go with rod pump from the beginning, you're going to face or you're going to deal with the sand. And I know Donna and in several classes, they already covered about plunger, cages, all the different ball and seat that you can use to handle a little bit of this. But again, it is a problem, and there is something, and there is different methods that we can use to address that. And let's start from the basic. So all the sand that, let's say in this case, it was already on the well because it was fracked, it was put in an ESP or gas sleeve, and we're receiving now that conversion to a rod pump. There is a portion of that sand that we need to lift to the surface. Dealing with that is more being able on the upstroke and the downstroke, the density of the sand or the heavy particles are going to fall down, being located on top of your pump. What it means in every upstroke and downstroke, those particles that are smaller on that clearance based on the design that you have from your rod pump are going to be located, and now slowly you're going to crush those back and forth until the point if you're shooting the well or something happened, you're getting a lot of sand on top of your pump, and it's going to be more challenging to be able to restart. Also, the buckling that you're going to cause in your rods. Every time that you're putting more weight on top of your pump, what you're doing is more pulling the rods just to one side, and you're changing that load effect that you got in your system. So that's something that we're facing every single day in a conversion well, and being able to deal with that portion of the sand and handle that prior to the ingestion of the pump. That's what we're covering today.
Right. So let's say we have your sucker rod pump and we're operating the pump just like Gustavo said. We have the buckling, and because of these sand particles, you're going to generate friction. That's what it will cause. Friction. It's going to go ahead and wear your rods. It's going to go ahead and wear your parts of your rod pump itself. And whenever we're seeing the pump cards, whatever we're seeing is we're seeing a lot of fluctuation, like we can see right here. is on the upstroke and downstroke is because we have so much sand particle now, so that the operations of the rod pump is not optimal to what it was predicted at. And then, go ahead, Gustavo.
No, one of the things like Donna did in one of the class when they were explaining about the pump cars, one of the things that you're seeing is more that friction. So all this interference that you're seeing over here is more the friction of those particles of the sand that is located between the plunger and the barrel, and it's just traveling up and down in your upstroke and downstroke. And I know you're going to cover this on the
right
next
here. Yep. That's exactly what we're going to just say is whenever you have that clearance, and we're seeing that sand particle right in between that clearance is exactly where we're seeing that friction on the pump card. And moreover that, we're going to have the packing off of cages and plungers, and we always hear that the pump is stuck, the valve stuck open. All of this is going to go ahead and cause a premature wear on the pump itself, just because there's so much sand particle, higher pressure, and now the production is not obviously producing yet what it's supposed to be.
And one of the things that also I would like to cover is like they always are talking about the clearance or what will be the right clearance or that space that I need to have between my plunger and my barrel. If I go too tight, what I can do is cause too much friction, and now I open that space, and now like 6,000 of the inch, maybe I can get too much slippage that I'm going to start to losing part of my production. So you always need to find that sweet spot that is going to give you, based on the particle size distribution that we're going to cover this later, but you need to understand that you need to give enough space for the sand or for some of the small particles that are coming back to be able to flow, either if you use a sand diverter or something on top that maybe can help you to handle that. But you need to identify if you're just having like 8,000 of the inch and your slippage is causing like 3 barrels per day that you're losing, that equal 30 days is going to be 90 barrels per day. With a 37 price oil, it's almost like $3,330 that we're almost wasting every month. That's what finding that sweet spot is going to be critical to avoid that word plunger or to avoid that plunger stuck in your barrel. And one of the things that we can see, there is multiple technologies currently on the market, and those are more like accessories, and some of those are more part from the pump, API, non-API, that is going to help you to extend that run life, and it's going to help you to control some of the sand particles either prior reach the pump or after it's traveling through the pump. So we can see different type of plungers that Donan already covered in several presentations, different type of cages. We see like kind of pre-packaged screen or gravel pack. We can see like far plunger. In some areas work, in some areas doesn't. Same thing for the desanders and also the screens. And I now the first thing when we see a screen is more something super tight and it's going to create a concern. Is I'm dealing with this amount of sand, for sure I'm going to plug the screen. So there is a methodology that we're going to cover. When you're using any of the system technologies, you need to understand a little bit of what you're facing with. And also we got the purge valve or the dump valve is something that is going to help you, is more to flush some of the sand that is located on the tailpipe after you start to deal with some of that treatment or previous handling part. And that's kind of like what you guys are maybe visualizing or maybe thinking in your mind when we discuss about the screens. First thing that you're going to think is more like it's going to plug, and for sure it will plug if you don't do the right diligence. It's the same thing with a rod pump. If you put the wrong pump in the wrong application, you're going to lose production, or you're going to face an issue either with gas interference because you're causing another problem. Pressure drop. I know people is always concerned about the pressure drop, and yes, if you're not sizing the screen appropriate with the right length, what you're going to cause is some pressure drop, and if you have some high scale tendency, what you're going to see some of the scale is going to start building around the face of the screen. But just to give you some numbers, I mean, a regular screen can have between 180 square inches to 320 square inches to handle either some of the 200 microns or 350 microns. What it means, you're going to get more open area in your screen than what actually you have in your standing valve. Based on the setup or the design that you have, your standing valve is going to have either 8 square inches or 12 square inches max. So you always are getting more open area on the screen, but there is a process for the fluid to go through, because through every single individual slot or window that we have on the screen, this is how you do the filtration. This is how you're going to be able to handle a portion of that. And if you try to filter 100%, this is what you're going to face, like the picture on the left side. You're going to plug the screen. If you have some paraffin issue, it's going to cause something like that. So having the right understanding of the problem is going to determine the success for the application.
And to champion what Gustavo just said is absolutely right. If we're talking about screens, the definition of screen is restriction through the fluid, right? And that's what we're doing. But how do we apply that is the main deal, that whenever we're applying to homogenize the fluid. We're applying to go ahead and give the pump what it can handle at that point. So that's what makes it really different, is the application of these screens, application on particular well conditions. And applications, like Gustavo was saying, if it has paraffin and we go with the tightest slot size, we're going to go ahead and plug the screen. If we go ahead and want to filter out 100%, we're going to go ahead and plug the screen. So just going ahead and analyzing what is the right application makes the whole difference. And then some of the other concerns regarding the sand is we're going to fill up the tailpipe as soon as possible, or as soon as it started producing. So that's something that how do we go ahead and design the whole wellbore that way we're not only filling up the tailpipes, we're also having some of the sand in the whole annular space. And then another thing is erosion. So we do know that with high production, we're going to go ahead and create certain velocities added on with the sand coming in. So if we have such high velocities that it's going to go ahead and now cut your sand or the sand separator, like we can see in this picture, there's going to go ahead and have a lot of sand erosion in the sand tool itself. So how are some of these common concerns that we're going to go ahead and address and say what is the most optimal way to go ahead and design, not only for the production, but also go ahead and have more retention time of the whole BHA?
And yes, on like the photo that you was mentioned on the right side, like the erosion. I know we got one call from one of our customers in the Bakken, and he was talking about, hey, I just went with a desander, but this is what happened to my desander. And, the desander is designed to be able to take all the fluid with the sand, spin the particles around the sleeve, and send some of the sand to the tailpipe. As soon as you're filling all the tailpipe, even if you go 4 or 5 joints, if you do the volumetric calculation, filling those up is so easy. More if you get hit by a frac well, you can fill those up in less than 10 minutes. And what you're going to face now is just reaching the sand until the top section of the last tailpipe joint, and now it's too close to the helix, and what you're going to see is now all the forces is going to spin just in one specific point, and that's where you can see that erosion is more. The desander is doing their job, creating that centrifugal force and spinning the particles, but the problem is now the force or the wave that you're creating to be able to spin the sand is not dissipating because it doesn't have any room to go. And what you're doing is just spinning in the same spot over and over and over, causing a sandblasting that is going to relay on the fissure either to a failure because you're going to cut that desander out. And it's a common issue. We see those on ESP as well. That's what the design is so critical for any of the accessories that we use to handle any type of sand issues. And one of the things that we talk about like criteria, we talk about that we need to understand a little more of the mechanism or the concept for the sand control. So the first thing that we always tell people, you need to understand and you need to recognize with what you're dealing with. So the majority of the time people is like, yeah, we normally use 20/40 or we use just 100 mesh with a little bit of 40/60. Yes, that's the frac set. Once you are fracking the well, you're almost breaking those particles, and you need to understand the particle size distribution, because all the sand that you frack in the well is now coming up with a little bit of formation sand, and that's the sand that you're going to face in your pump. So if you can get a sample in any of the tear down that you're doing from your rod pump, try to get a sample of the sand. Try to get a sample from the tailpipe. In that case, you can understand more what is the sand that is going through my system, and you can differentiate what is the sand that is going through the tailpipe and what is the sand that actually is going through the pump and is causing that plunger to get stuck on my barrel. So it's going to be a different particle size, I will guarantee you that, and that's how you can start to understand how I can handle that. What kind of method can I use to be able to unplug the screen in case that you want to do that, and be able to filter a portion of that, but at the same time being able to allow some particles to go through. Now the pump can handle that. Any design, any screen is going to be 100% filtration. If you try to do that, you're going to plug it. You always need to do between 60 to 75%, and those numbers will change based on the viscosity, the inorganic deposition, that means the scale tendency that you get in your well, the organic components, like if you get a lot of asphaltene or paraffin, the corrosive components, if you're dealing with a lot of iron sulfide, also the amount of fluid that you're sending through, the total production, the water cut. It's not the same thing that you're dealing with 80% water cup or 25% water cup. So what the oil is going to do based on the viscosity is going to trap some of those particles, and that's what the concept of homogenization starts. You need to be able to handle, because all the sand is going to be agglutinated, causing some chunks going through. It's not going to be particle by particle. And also the capacity of the first stage or the type of method that you're planning to use. How much sand I can filter either with my screen or my desander, and how much sand now I'm sending to the point of the slippage of the pump spacing, and also of the clearing that I need to have between my plunger and my barrel. Try to avoid the pressure drop, and also based on the, if you're dealing with a conventional or unconventional well, it's more also where you're landing the equipment, the inclination and the dot lead, and try to understand a little more of the entire BHA. So many of you guys have going to the tear down. Many of you guys has been seeing, yes, we're dealing with sand, but when the production engineer or the operator is telling the service companies we're dealing with 100 mesh, or we're dealing with just 40/60 or 30/50, this is what people is thinking. It's more the photo on the right that you're seeing just particle by particle. But in reality, when you're pulling the well, when you see everything on the tailpipe of your pump, you're seeing is more the picture on the left. You see a lot of sand that is agglutinated, that is just mixing with the oil and is trapped, and it's more like a big chunk that is going through. So when you're doing any type of filtration, the sand that is passing through your screen or your desander is the one that you have on the left. After you dry the sand and you analyze to do the PSD, that is the particle size distribution, it becomes the picture that you get on the right. And again, this 100 mesh or 200 microns or whatever will be the size is just the size of the particle. It doesn't mean that it's the size of the particle that is now trapped in the oil, because now it's going to almost increase 2 or 3 times that size to be able to pass through your pump, through your standing valve, and to fall back and start to be located around your clearance.
And so now the question comes on is, we do know that these are the sand problems. We do know that these are the common concerns that is that we're facing day to day. And now that Gustavo has gone through what is the particle size distribution and what are some of the concepts that we need to go ahead and have before we go ahead and design the well, the question comes in is how do we effectively separate the sand? So that's what exactly it is these days with more of the unconventional wells, we're not going to see sand just in what we're thinking. It's going to come in slugs. So whenever we have those sand slugs coming from the horizontals, how do we go ahead and effectively distribute this? Is we call it the two-stage filtration, or just so that we can homogenize the fluid, is that let's go ahead and use the whole wellbore. Let's go ahead and filter the bigger chunk of sand particle. Let's go ahead and also filter the finer sand particle and dump it in the tailpipe. And then another portion would be something that the pump itself can handle. That way, we're utilizing the whole wellbore, we're homogenizing the fluid, and now we're effectively distributing the sand particle. So to do this, in the first stage, we have the sand screen, which is a V-wired screen. So if we can see right here, the screens are in the shape of a V screen. And the space in between each wire wrap is the slot size that we're seeing. So we can see that externally, we're going to definitely get that particular sand filtration. Internally, the open area is 2.5 times the open area of the conventional screens that are used. Also, below that is we have the Vortex sand shield or a desander. So whenever we have a combination of formation sand and frac sand, we're going to go ahead and filter out with the first stage in the intake, and then with the minute sand particle going in the helix, creating that centrifugal force, gets dumped into the tailpipe, and the remainder comes into the dip tube along in the tailpipe, in the pump.
So just to be sure and revisualize again the photo that we saw before. One of the things, if you see on the photo on the right side, where Chibani was talking about the screen and the B wire and the B shape, you can see several particles of sand agglutinated, and that's what it's going to do. When the sand is going through the screen, mixing with the fluid, what you're going to see in that point is more a coalescent effect, and some of the particles are going to start hitting that screen jacket back and forth, back and forth, back and forth, until you're breaking part of that agglutination of those chunks, and now particle by particle will start to go through the system. So what you're doing is not like all the sand is falling back to the rat hole or the lateral section. That is not going to happen. A big portion of the sand is just going to keep suspended in the fluid, and it's just coming back and forth through the screen jacket. So the main deal with the screen or the homogenization process is more delaying the time. So if you don't have anything, and let's say you just go with your rod pump, open tubing, what you're going to see is all the sand, all the chunk is going to go through the sanding valve at the time. In this case, what you're doing is just start to slowly breaking that agglutination and allow just small batches of sand to go through the system, and it's going to be a minor portion. So instead of you're dealing with 100% of the sand at once, you maybe are just facing 5%, 10%, and you're just delaying the process. You're not dealing with everything immediately, and that's what can cause an issue. A rod pump can handle the sand, but if you try to get all the sand at once, you're going to plug either a rod pump, either an ESP. So either PCP, we see in Canada, we see in Colombia, PCP just getting plugged and stuck due to the amount of sand that is traveling at once. So that's part of the concept, and that's what we really want to emphasize to you guys is more how the sand behave when it's mixing on the fluid, and how behave when it's going through the screen or any filtration media that you have to handle the sand particles prior to go through your pump.
And so that's exactly what is important here is after doing the sand sieve analysis, where we can see what is the particle size distribution of the dry sand, and going ahead and taking into consideration the well conditions, What is the deviation? Does it have any scale issues, paraffin issues? How many interventions has the well had? Depending on that is what we go ahead and would select a slot size to go ahead and efficiently filter out, but also to go ahead and efficiently apply at that particular well condition. And then that would also come in place with the length of the tool, is depending on what is the production, what is the water cut that we're talking about, what is the oil viscosity. Here in the Permian Basin versus Bakken, we're talking about two different things. So the slot size here versus there would be completely a game changer. So all those things would matter. And one most important thing is the pressure drop, is something that we always talk about, is so critical to go ahead and analyze that with the well conditions, what are the pressure drops that we go ahead and analyze before we'd go ahead and do the homogenization of the screens.
And one of the things that we see about that concept is more, again, we need to go with calculation. We need to run some numbers to be sure that you're not prematurely plugging the screen, and either you're not going to cause any erosion or damage on the outside jacket of the screen to destroy that system. So that's why, based on the production, what you're going to determine is the particle velocity for the fluid as well from the sand. And having that in consideration, we get a correlation based on the API, viscosity, water cup, and the amount of fluid that is traveling through the system, and how much is going to be that agglutination or that percentage of the sand that is going to maintain more in the fluid, and how much you need to be able to break that out. So in this case, we see just a quick example of 400 barrels per day, and the pump is operating 100% at the time. Why the runtime is an important factor. It's not the same thing, even splitting those 400 barrels per day is a little more even, that my well just operating 50% of the time and producing the 400 barrels per day. What I'm going to see in the upstroke is the drawdown is going to be much higher, and I'm going to face more force or more drawdown going through the screen, through the system. What is going to cause is an increase on the velocity. So that's why we try to keep those numbers based on the opening of the screen. We try to keep those numbers below that limit to be able to avoid that plugging. And one of the best analogy that one of my professors was telling me one time is more or less saying that it's a fire. And wherever you guys are in one room, is we got 10 people in this room, and all the 10 people try to go at the same time. When you're going to cause, you're plugging that door and everybody will die. What if the right way to do it, or the smart way to do it, is one at a time? And that's kind of the concept that we need to use with the screen. Try to force that fluid to start to go through multiple windows or multiple doors. So in that case, you are spreading out that pressure drop, and we try to keep everything below 1 psi. In that case, you are not creating any high delta P that it can cause on the scale to build up, and at the same time, you are allowing all the sand particles to go through. And that is part of the calculation that we do based on the same concept. And the length of the screen and the opening that you get and the percentage of the total fluid, water cup, API, everything that we discussed before, how much pressure drop I am causing through the system. In this case, you can see for a 682 barrels per day, 80% water cup, an API around 41 is more like Permian. We can see that if you have a 48 feet, that means 2 sand screens, you're going to get 0.09 psi of pressure drop. That's nothing. The point that you're going to see more pressure drop is normally your standing valve, because that's where I'm communicating all the fluid that I'm sending through the screen or through everything now through my pump. That's where we normally see higher pressure drops.
And also to go on lines with that is the selection, like we talked about again, is your particle size distribution. Based on that, in this example, we can see the distribution that is the highest in 305 microns. So whenever we're going ahead and sizing the size screen, we do have to take into consideration all the well conditions and see that this is the dry sand that we've dried out, and this is the dry sand particle size distribution. So anything to go ahead and filter out 305 micron sand size particle is something that we'll go ahead and design considering the well conditions as well. And depending on the failure rates, that's where we have is, let's say we have failure rates less than 3 months, or the failure rate is in between 3 and 6 months, or it's greater than 6 months, depends on the factor of what slot size is needed, as well as the particle size distribution right here. So that's what comes up and makes up the two-stage filtration. The first would be your sand particle size distribution by your tubing screen, and the second would be your vortex sand shield or desander, and that's what we can see is using the whole of your wellbore. We're going to go ahead and filter out your sand particle size in the annular space, go ahead and have that centrifugal force effect and dump into the tailpipe, and effectively distributing and homogenizing the fluid as well. And also, just to go a little bit deeper into the desander, which most of you guys would be familiar, but since we have a variety of audience, I believe some of them are students too. Whenever we're talking about desander, what is a desander is we have a body which has a part called helix that goes ahead and creates a centrifugal force. That means that your fluid goes ahead and spins around and creates that velocity to filter out your minute sand particle into the tailpipe, and then the cleaner fluid that goes through the dip tube, which is attached in it. Also, in this particular one, the Vortex, we have a sleeve on the outer body just in case there's a lot of erosion, a lot of sand damage that's caused in the descender itself. And let's say you have a fishing job, you do have an outer sleeve that's going ahead and protecting the integrity of the tool itself.
So this is more like an overview, or kind of like bring everything together about the two stages and versus one stage. If you guys have been getting some good luck with just a regular desander, I mean, you're going to consider it that what you're doing is all the sand that you have in your wellbore or outside, you're just dumping everything inside the tailpipe. That's what sometimes you guys get frustrated and feeling like, oh, I am filling all the tailpipe too fast, I need to do something different. Regardless what you do, is you go back with the same thing. It's more like a deja vu. You're doing same thing over and over. If you use the two stages filtration, the benefit that you can get is instead of filling all the tailpipe at once, or let's say in 3 months, you're now selecting which particles do you want to go through the screen, through the system, which particles actually do you want to spin out and located in the tailpipe, and which particles do you want to send through the pump. Just to put some number, in a well that is producing 100 mesh and some of the 40-60, what you can see is more having the two stages filtration. You can get around 40% of the filtration with the primary stage, that is going to be just the sand screen. You're going to get another 40% just going through the tailpipe with the desander or the Vortex, and you get 20% or 10% based on how you sizing everything just going through the pump. So the analogy is, if you're going with a desander and you get in 3 months, you can double or triple the runtime because you're handling the particles prior to reach the system. If you have your currently rod pump and you're achieving 1 year without anything, but you're still dealing with a lot of sand, using this methodology is going to give you the opportunity to increase the runtime and allow less damage through the system, less buckling, less wort plunger, less damage in the barrel, and you're not going to plug that system so fast, and you're going to be able to increase the runtime. And that's something that we all need right now, being able to operate our wells with the less expenses and being able to get more profitable per well. And that's part just like the distribution based on the slot sizes. So every single well is different, regardless that you use a similar frac sand or you already identify the formation sand that each well is dealing with. We always recommend to take the samples and analyze these this is going to determine the right approach that you guys need to use based on the issues, and you can play with the lane based on the necessities and the total production. We can email you some of the calculations that we use so you guys can do everything in your own, but that's kind of part of the science behind this.
And then obviously the second stage is your vortex sand shield. Again, depending on the particle size distribution, especially the frac sand size that we're using these days, 100 mesh or 40-70 combination. This is where the centrifugal force comes into play and goes ahead and generates that force to go ahead and distribute the sand particle into the tailpipe. But the combination of the first stage and the second stage, where we have a particle size distribution of bigger slot size or microns, and then the finer slot size or microns, is where a combination would be most effective. And this is the lab test that we've done, where we can see that we've go ahead and dumped different sand size particle, and what we can see right here is the helix. This is the descender, inside is the helix, and we can see right here that the centrifugal force is generated, and below is what we can see that the sand particle is now dumped at the end, like right here. And that's exactly what we've been talking about, is that centrifugal force to go ahead and spin the particle and go ahead and separate it.
You know, this reminded me, we got, it was like 3 months ago, we got a call for one of our operators that they used to have one of those systems in the ground, and in one of the wells, he normally have more 912 pumping unit, and he operated normally 168 stroke lane, and everything was working perfect. Everything was fine. And after that, in some of the new wells, he was doing some rotaflex, and he was like, hey, you know, one of the things that I don't see is like on these wells, regardless that it's producing the same thing, I don't see that higher efficiency on the filtration, and I don't think that fluid is creating that, or that helix is creating that centrifugal force enough to be able to keep some particles in the tailpipe. So we was just talking back and forth, and we said, you know, from the beginning, like, if you're changing your pumping unit, we need to understand like the difference between just a conventional pumping unit versus a rotaflex. The drawdown that you're generating is going to be higher due to the long stroke length that you're using, and that's going to change the dynamic. In cases like that, what you need to do is just downside that helix. We always give you some ranges that you guys can play with, but in cases like that, you need to go one size under, just to be able that you're creating a little more centrifugal force and closing a little more the veins on the helix to be able to generate the force that is required to spin the particles. And just as more changes like that is going to give you the efficiency that you guys are looking for. And that's the same thing. Either it's a basic descender or it's something in combination. You need to play with the conditions of the well, plus look the well for the entire system. What is the pumping speed that I have, a stroke length, type of pumping unit, that is going to determine any sand control method or gas separation method to be efficient enough to handle what you guys are expecting for.
Hey, Gustavo?
Yes, sir.
I have a question here for you.
Yes, sir.
Because I'm sure there may or may not be some folks out there though too. So I would be curious, because I know, for any of us, and I know Tom Bill's on the line too, some folks here, anytime, at least for people working with pumps, get the feeling most times that there are numerous ways to try to combat, these downhole solids and downhole gas. And there's all kind of options out there. And just for any of the operators out there, could you at least maybe share, because some of these people are in California, some are in Canada, some, everybody's dealing with different wells here. Where would you say you found, just in these certain well conditions, in this certain region, whatever it be, that says this is where we really find success more times than not? It's not to say that you don't find success in other areas, but where's a good sweet spot that you feel like these screens and your double filtration really come through in the clutch?
So I will say it will be more related on how much information we can get. Let's say just on the Permian Basin, understanding frac sand and all those conditions is going to give you the right opportunity. Doing the right filtration over here with the light oil that we have is so easy to filter those particles, and it's so easy. I will say the best success that we can get is either Permian and Delaware Basin, because it's so easy to deal with the sand based on the viscosity of the oil. It doesn't mean in heavy oil you cannot deal with that, and we get some customer in California, but the challenges or the dynamic that you need to apply to be able to do that filtration now is going to be a little different. Like in cases like that, we don't try to use the combination of the two stages. If you get a lot of heavy oil, we try to do just open that gap of the screen and go like 125. It's super big, and the only thing that you want to do is just being able to handle more the bigger chunks that is causing with that fluid when it's passing through, because it's more like getting like peanut butter going through the screen. It's so viscous that any sand can cause issues in your rod pump. So that's what we try to do. It's a different dynamic. It's not a filtration anymore. It's more homogenizing the fluid prior to the ingestion of the system. I hope that answered your question.
Yeah, no, I mean, definitely at least helps to kind of point folks and understanding that, I mean, because one, it's a problem and everybody has to deal with it in some form or fashion, and there's no one silver bullet out there, right? But everybody's just trying to keep it pumping as long as you can, so.
Yes, sir. And that's part of what we have for the presentation today. I don't know if there is any question additional from the people in the audience. If there is anybody that has been facing concerns about plugging the screens, or, that's something so common. We always hear that, the screen doesn't work, it plugged. We go back, we kind of explaining why it didn't work, and we ask, you guys analyze the particles that you try to filter? No. Did you guys size everything based on the production? No. We just pull one screen that we have in the jar and we just put it in the well, but it didn't work. So it's more like just getting, like you say, one silver bullet is not going to solve all the problems. Maybe it will work in some areas, but you cannot take Tylenol for all your problems. You need to get a little more deeper analyze in case that you want to increase that runtime.
Well, and if there aren't any questions, definitely I would recommend people take this contact information that's here too. By all means, please reach out to these folks, even if you've run into some problems and it didn't work for you. Maybe just reach out to them, let them know why it didn't work, and maybe they can help you out. So I appreciate the time, Gustavo, Shivani, both you guys, everybody on your team.
Yeah, thank you, Jason. And thank you, everybody, for your time as well and listening to this presentation.
Thank you, guys. Have a good day.
Thanks.